So far, all of our hypothesis tests have involved a single population parameter. So, for example, we had null hypotheses that would be about the sample mean. But it often arises in practice that we need to be able to compare two things. So we might have, let's say we've got this population which consists of the daily output of, let's say, factory A, and then we want to compare it to the daily output of factory B. So we have all these observations coming out of here, and we've got all these observations coming out of here, and we want to know, are they significantly different? And whenever it comes up that you have to compare two populations, you're going to compare two populations, we're going to be doing t-tests. And there are two different kinds of t-tests. There's the independent samples t-test and the paired samples t-test. In this video, I'm going to go in depth and show you an example of an independent samples t-test. And we're going to deal with the paired samples t-test next time. But examples of where an independent samples t-test comes up. Anytime we have two completely different samples where we cannot match something from one group to another, we call these independent samples. So for example, let's say we want to compare, okay, there's that word. We want to compare two shifts in terms of their accidents. So we have, the day shift, and we've got the night shift. So once again, we've got, all these. Okay, so all these shifts that were completed during the day, and then all these shifts that were completed during the night. And these are completely different from each other. I mean, there's not really any way to like match one here up with one over here. Okay. Another example of an independent samples t-test might be like, let's say you wanted to compare two different let's say software development techniques. So we've got traditional software development technique is the waterfall. Okay, so we've got all of these software projects that were created under the waterfall method, and let's just say we have some measure of success, from 1 to 100 versus agile. And you wanted to know, is there a significant difference in the success of software projects completed under the waterfall method versus the agile method? So once again, we see that these are independent samples, right? They're two different populations because there's no way that we can actually just match up one with another one in the other population. Okay, so these are the cases where we're going to do independent samples t-test. Now, as a little bit of a preview, in contrast to that, when we have paired samples, usually what we're doing is some kind of before and after, where we're going to have, let's say we've got employee A, B, and C, and this was before, let's say before raises. Let's say their level of motivation before a raise versus after a raise. Let's say after. And then we've got employees A, B, and C. So in this case, we can actually, track, this person from this before case to this after case. So person B from before and after, and person C from before and after. Okay, so when we can match an observation in one sample to the other, then we're doing a paired samples t-test. But if we just have this situation where we're just comparing two groups, two populations, then we're going to do an independent samples t-test. Okay, and that's what we're going to do in today's lesson. Okay, so with independent samples, remember that the key difference here is that originally we were just making a hypothesis about a single population parameter. So we're just saying that it's like this. Okay, so this is just one parameter. But now we're doing something a little bit different. We're trying to compare two different populations. So we need to incorporate parameters about both populations. Okay, so let's see if I can draw this. Let's say we're going to compare, factory A and factory B. So, let's say, this is the output of factory A. Let's just say it's, 100 units per day. Okay, and this is what its distribution looks like. Okay, so that would mean that 95% of the time, its output will fall, between these two levels. Okay, so these, let's say, got critical values here and here, and 95% of the area in here, 95% of the area is between these 2 points. So that means that its output is going to range from here to here 95% of the time. Now, let's say, on the other hand, we'll just put it on this same diagram. We've got factory B, who has an output that looks like this. Okay, so this is going to be, so this 100 is the center of the factory A's distribution. And this, whatever this is, I don't know, let's say it's 108, is the center of factory B's distribution. And so it's 95% of the time, its output is going to be between here and here, let's say. Okay, so we see that there's going to be an overlap between these two. And the size of this overlap is going to determine whether or not we can say that there's any real difference. If the overlap is very large, then we can say that there's a negligible difference between the two. It's not significant. If, on the other hand, the overlap is very small, then they are definitely drawn from two very different populations that are centered on different places. Okay, so we have these two populations with their own means, and we want to test if there's a significant difference between them. Okay, so our null hypothesis. So remember, we always start off with a null hypothesis. So a null hypothesis with an independent samples t-test. So we're going to have a number of possibilities. So it could be that we are hypothesizing that the mean of both populations is the same, okay? Which would mean that the alternative would be that they are not the same. Now, I can rewrite this slightly by doing a little bit of algebra and say that, so hypothesis H naught, null hypothesis, is also saying if H1 minus H2 is equal to 0, right? So all I did was I subtracted mu2 from each side. And I'll do the same thing with the alternative, and that would be mu1 minus mu2 is not equal to 0. Okay, so this is one form that the hypotheses can take. So notice once again that because it's two populations, we're hypothesizing about the relationship between two population parameters. Okay, so another case that we could have here is if we're going to do a directional hypothesis. So in this case, we might say, okay, we might think that we might have some reason to believe that the population mean for the first population is greater than or equal to the mean for the second population, making the null mu1, making the alternative mu1 is less than mu2. And if I rewrite these again, just subtracting mu2 from each side, mu1 minus mu2 is greater than or equal to 0. And the alternative, mu1 minus mu2 is less than 0. Okay. So there's another way that I might write these. And so we went over last time about why you might make a directional hypothesis, that is doing a less than equal to or greater than or equal to in your null. If you have some claim, like, if you have a suspicion that the first factory, for example, is producing less than the second factory, then you want to set up your alternative like this. Okay, let's go over the third case then. It's going to be very similar to this one, but might as well do it for completion. Okay, so if we think that the direction is going the other way, that is, if we think mu1 is less than or equal to mu2, making our alternative hypothesis that mu1 is the opposite of that, greater than mu2. Okay, we do subtract mu2 from each side again. Mu1 minus mu2 less than or equal to 0. And mu1 greater than mu2. Mu1 minus mu1 minus mu2 is greater than 0. Okay, so there are three different ways that we could set up our null and alternative hypotheses under the independent samples t-test. So this would be, of course, the two sample, and these would both be one tail test, or sorry, not one sample. These are this is the two tail test, two tail, and these are each one tail. And so this is, because we're concerned with the alternative being the, well, basically these are both right. These are both one-tail tests. So we're going to be using the t distribution. So the reason why a two-tail versus a one-tail makes a difference is in how we compute the p-value or the critical values on the t distribution. So we're going to go through an example, and so we'll see one tail versus two tail, but we'll go ahead and do that. Okay, so we're going to take a look at how it is you compute a t-test by looking at this particular example. Okay, so we want to know if the location of where exactly you put beverages in a grocery store actually has an effect on their sales. Okay, so you're a sales manager and you want to know if there's a difference between two different kinds of end caps. Okay, so the end caps are those shelves on the ends of the grocery store aisles. Okay, so you have two choices here. So we want to know, okay, we've got a produce. So we've got one end cap near the produce department, okay, and the other at the front of the aisle that contains the other beverages. Okay, so basically we've got a produce end cap and we've got a beverage end cap, and we want to see, do sales differ significantly? Okay, so we've got this this classic independent samples issue where we've got two distinct populations. We've got the produce end cap sales and we've got the beverage end cap sales. And we want to know, okay, is this mean significantly different from this mean? Okay, so just to go through some of the details here in setting up the study. So you select 20 stores from the chain, okay, and you randomly assign 10 of the stores to sample 1 through 10. To sample 1, and 10 to the stores in sample 2. Okay, so in the sample 1 stores, you'll place the cola on the beverage end cap, and in the second sample you put them on the produce end cap. Okay, and at the end of the week, sales will be recorded. Okay, so now we want to determine, okay, is there a significant difference in the sales based on where we place them? Okay, so there's the problem setup. I'm going to go ahead and start off by doing the hypothesis test step by step, just like with the single parameter case. When we're doing just like the single sample case, we're going to be using the same steps of hypothesis testing to make sure that we're drawing the correct conclusions. Okay, so step 1, we have to identify our hypotheses. Okay, so what do we know? Okay, do we have any basis on which to say that we have a directional hypothesis? And we don't really know. We just want to know if there is a difference. So we'll just go ahead and, lacking any other information, we'll just set up our null as saying, okay, this mu1 is going to, I guess we can define mu1 as the beverage end cap mean, and mu2 as the produce end cap. Okay, so our null then is going to be that the difference between these two is equal to 0, and our alternative is that it's not equal to 0. Okay, so it's going to be a two-tailed test. Okay, so 2, we need to specify the desired level of significance and our sample size. Well, we already know, we've already been given the fact that we have 10 stores with one and 10 stores with the other. Okay, so we actually have two different sample sizes here, right? So we've got 10 in one sample and 10 in another sample. And desired level of significance, well, let's go ahead and set that equal to 0.05, same as before. Okay, all right, so now we have to determine the sampling distribution and the test statistic. Okay, so this is going to be a t distribution, and we're going to be doing a t statistic. Okay, and how exactly we go about calculating that, now that's what's new, because calculating this particular t statistic for this difference is different from how we just did it before. Okay, so I'm going to show you the formula for it, and then we're going to go ahead and implement it in Excel. And then we're going to, of course, Excel always has a shortcut. So then after we calculate it once by hand, I'll go ahead and show you how to take the shortcut and do it in Excel. Okay. Okay, so the t statistic. So exactly how you calculate this t statistic for this test is going to be determined by whether we can assume that the variances between the populations are equal. Okay. Now, at no point in this course are we going to handle this case. We're not going to bother with unequal variances in this particular course. So all the questions that we're going to be addressing are going to be this particular case where, okay, so we've got our independent samples, and we're going to, we don't know the population standard deviations, but we are going to make the assumption that they are equal. Okay, we don't have any reason to not believe that, so we'll go ahead and take it. Okay, so starting down here then, so we're calculating the test statistic by looking at the difference between the sample means and then subtracting it from the hypothesized difference between the two means. Okay, now notice that our hypothesized difference, okay, is 0. So we don't have to worry about this part of this because this is just going to be equal to 0. Okay, so we're really looking at the difference between the two, and then we're dividing it by something. Okay, and in the parentheses here, this is just the sample size of the first and the sample size of the second. But we have this other figure in here, which is what's called the pooled variance. Okay, so S is going to be the sample variance. Okay, S squared means sample variance, and then this little subscript here for P means that it's going to be pooled. Okay, and this up here shows you how to calculate this thing down here. So you have to calculate this first because it's a necessary component of this down here. Okay, it looks involved on first glance, but as we'll see when we're calculating it, this goes quite quickly. Okay, so now that we've got we've got kind of the hypothesis testing set up, let's go ahead and actually calculate the value of the test statistic now by looking at the data. Okay, let me see if I can line these up so we can see both of them. Okay, so this is our data then. We've got observations 1 through 10, which calculated, which recorded the sales of the sodas that were on the beverage end cap. And in the green, we've got observations 11 through 20, which are on the produce end cap. Okay, so these are our two different populations. Okay, so now each of these variables here, I've set up a blank where I can put them down here, because if I go piece by piece, it'll be very easy to just start plugging these in. Okay, so N1, so up here, this is just the sample size of the first sample, so that's just 10, and the second sample was size 10 also. Okay, X1 and X2. Okay, so what are these? So this is up here. So X bar 1 and X bar 2, these are just the sample means. So let's just find those sample means then. So this is going to be, so X1 is going to be equal to the average of, move some of these things over here. the average of these. Okay, so 50.3. And then x2 is our other sample average, so we'll do average of these. Okay. All right, so we can see that the produce end cap appears to have a higher sample average, but once again, because we don't have a concept of what the variance and confidence intervals are, we can't say whether that 72 is significantly larger than that 50.3. Okay, so now we have to go ahead and find our the variances within each sample. So if we look at here, so in order to calculate the pooled variance, we have to have the sample size and then the actual variance of each sample. So this is the variance of the first sample and the variance of the second sample. So notice how this is really kind of like a weighted average. So we're multiplying the variance of the first sample times the size of the first sample minus 1, and then adding it to the variance of the second sample times the size of the second sample minus 1. So let's go ahead and find those sample variances then. So this is just going to be variance. So in Excel, variance is var, and we're going to use S because these are samples. We're treating them as samples. So the variance of these, okay, all right, so the variance of the first sample. Now we're going to do the variance of the second sample right over here. Okay. Okay, so now we've got these, we can calculate the numerator and the denominator of this. So the numerator is just going to be this. The denominator is going to be this. So let's see, the pooled variance numerator. So this is going to be equal to, so N1, which is up here, minus 1. And we'll put that in parentheses. Actually, put the whole thing in parentheses. No, it's not. Okay, and then this is going to be times the variance of the first sample, okay, plus now the size of the second sample, which is 10 again, minus 1 times the variance of the second sample. Okay, so there's our numerator. Okay, so now we just need to find the denominator. We could probably do this in our heads, but let's just go ahead and do the math. The size of the first sample minus 1 plus the size of the second sample minus 1. Okay, so 18. So our pooled variance will just be that division. So we'll do equal to this divided by this. Okay, so our pooled variance is 254. So all we've done so far is calculate this that we can plug into here. Okay. So now we're going to calculate the value of our t-statistic, doing the numerator, then the denominator, and then we'll be doing the division. Okay, so the t-statistic numerator looks like all we need is the difference between the two sample sizes. So I'm just going to do x1 minus x2, or x bar 1 minus x bar 2. Okay, the denominator is a little bit more involved because we have to take the square root. Okay, now we've got to get that pooled variance. So we're going to get that pooled variance right here that we calculated. And we're going to multiply it by 1 over, go ahead and do 1 over this N1, so sample size 1, plus 1 over the size of the second sample. We'll close all those parentheses. And okay, let's see, make sure we got everything we need here. Okay, square root, pooled variance times that sum. Okay, so now we'll take the value of the t-statistic by just dividing the numerator, dividing by the denominator. Okay, and we have a t-statistic of -3. Okay. So now what we have to do is figure out what we do in terms of the null hypothesis. So let's do this using both the critical value method and the p-value method. So we are using a t-statistic here. So remember, in order to find out the critical values of a t-statistic, critical value on a t-distribution, we need to consider the number of degrees of freedom. Okay, so notice that down here on the slide, it says that this particular statistic as calculated follows a t-distribution with degrees of freedom equal to the sum of the sample sizes minus 2. Okay, so we see we've got n1 plus n2 is 20, minus 2 is 18. Okay, so we'll start off by finding our degrees of freedom. Okay, so how do we find the left critical value? Okay, so remember that the t-distribution looks like the normal distribution, is just a little bit wider depending on the number of degrees of freedom. And so we need to find a left critical value and a right critical value when we're going to do a two-tailed test, as we are here with the alternative of not equal to. So let's go ahead and find the left critical value. So we'll do t in. Okay, so our probability, we wanted to be 95% sure, so that leaves 5% in the tail, so 2.5% in the left tail. So we're going to do 0.025, and our degrees of freedom was just up here. Okay. Okay, so our left critical value is -2.1. Now, I can right away say, well, I know that the right critical value will be +2.1, but let's go ahead and calculate it the same way. So we're going to do t in. Okay, probability now is 0.975. Once again, same degrees of freedom, so it's the same. Okay, symmetrical distribution. So what this is telling us is that for 95% confidence level with 18 degrees of freedom, that anything less than -2 or greater than +2 is outside of the acceptance region. So it's going to be rejected if it's beyond there. Okay. All right. So let's go ahead and rather than figure out the p-values right now, let's go ahead and make our decision. So we see that our t-statistic is here. Okay. It was -3, that these were our critical values. So we see that -3 is less than -2. So our decision is to reject. Okay. Now, what's the managerial conclusion? Now is where we have to step back and try to remind ourselves, well, what were we actually trying to figure out with this hypothesis test? Well, let's go back to our hypotheses. So our original hypothesis was that mu1 minus mu2 was equal to 0. And so basically our null was that the sales of these two are the same. So the sales of the soda are the same whether you put it on the beverage end cap or the produce end cap. And so the managerial conclusion then is that sales are not the same on the different end caps. Okay, so there's the managerial conclusion. Now, we'll come to the same conclusion if we do it with the p-value method. So I just want to go through the p-value method one more time, just in case that's an approach that we want to take. So remember, it's two-tailed, so we need to combine the p-values for the left and the right tails. So how do we find the p-value? So the p-value is going to be, remember that to find the critical value under t, we used t inverse. Now to find to go the other way, we just use the t.dist, okay? And our x value is going to be the actual value of the test statistic. So we'll have to put, we'll select that there. And our degrees of freedom was 18. and we always put true here. Okay, so 0.0034. Now, even though that's the p-value of the actual test statistic we've got, we also have to take that area on the other side. So it's going to be we're gonna have to have a right p-value that is the same as that, 0.0349, and the total p-value would be the sum of those, or we could just do this times 2. Okay, so the important thing here is that we see this is less than 0.05, our stated alpha. So our conclusion is the same. We go ahead and reject it. Okay. Okay, so that is the piecewise implementation of this formula here. Okay, so just to finish up this hypothesis test here, we found that the critical values were going to be, like -2 point something and +2 point something, and in our we calculated the value, the test statistic, as being -3 point something, and our conclusions were to reject, and so the managerial conclusion was the end cap. Now the end caps differ. Okay, so if we look at the actual output here, we see that so this second one was the produce end cap, and this mean sales is significantly larger than this mean sales. Okay, now as I said, I bring you through this exercise of actually going through and solving it by plugging values in, but Excel does this as a shortcut. If you go under the data ribbon and data analysis again, you'll see that there are a variety here of t-tests available to you. The one that we just implemented is the t-test, 2 samples assuming equal variances. And unless I tell you otherwise, for our purposes, we'll always assume equal variances. Okay, so if I select that, so variable 1 range, I'll click here and select these. Variable 2 range, I'll select these. Okay, now hypothesized difference, we take 0, okay, because that's what our null hypothesis had it. And I'm gonna go ahead and select an output range actually on here so we can look at the values. Okay, and then click OK. Okay, so this is gives us in one quick click everything that we did over here, and we'll see. Okay, so the mean for the first sample was 50.3. For the second one, 72. Here they calculated the variance as we did here of each of the samples. Observation, so this is N1 and N2. They calculated the pooled variance, which is what we did here. So we got the same value. And notice also they wrote down the number of degrees of freedom to be used in calculating the critical values and the p-values. So their t-statistic is calculated was looks like it's exactly the same as ours. Now notice that it found it. Okay, so it used a. We didn't calculate the t for one tail. We just did the 2 tail, and we found that it was 2.1, and so that's what they were doing here. So they just calculated the right critical value for the 2 tail. The p-value for the 2 tail, they got 0.006, and so that's what we got over here too. Okay, so we went through quite a lot of computation to get to here, but hopefully that clarifies what all of these different things are. But really, in the real world, you make sure that you collected your data correctly, and mostly you're just going to look in this case at this. Okay, and you see your p-value is less than 0.05, therefore you reject the null hypothesis that they're the same, and we can see that the second sample has significantly more sales than the other one. Okay. All right. So in the next video, we'll look at paired samples.